Hi again. In this, the second of the network videos dealing with trees and spanning trees, we deal with two algorithms through which we can identify spanning trees with minimum weight. These are Kruskal's algorithm and Prim's algorithm. The methods show a systematic approach to ensure numbers are accounted for without changing or writing over the top of previous numbers. We established previously that a spanning tree is a tree linking all vertices in a network without creating any cycle. And the sum of the weights of each edge of a spanning tree gives us the total weight of a spanning tree. We use the total weights to compare different types of spanning trees within the same network. The question therefore arises, how do we identify the spanning tree having the lowest value for the total weight? That spanning tree is called the minimum spanning tree. There are two common approaches to finding the minimum spanning tree. They're referred to as Kruskal's algorithm and Prim's algorithm. Kruskal's algorithm is based on edges, whereas Prim's algorithm is based on vertices. Kruskal's algorithm finds a minimum spanning tree for a connected weighted graph by adding edges of increasing weight at each step. It continually takes the next lowest weight, and so it's called a greedy algorithm. Not all edges are used in a minimum spanning tree, just a subset of the edges in the network, but every vertex in the network is used. So here we have a network with the weights for each edge in purple, and we want to find the minimum spanning tree through that network. So step one, in a table of two columns, write down the letters for the edge of smallest weight and the weight itself. So we look at all the purple numbers and we find that BD has a weight of 1, so we write BD and a 1. Then we write down the letters for the edge of the next smallest weight and the weight. Now we look at our diagram, we have 4 edges, each with a weight of 2. So we just pick them in any order. AB is 2, BE is 2, CF is 2, EF is 2. So we have those down. And then we continue in step 3 to listing edges in ascending order of their weight. So the next highest weight is CE and DE, and both of these have a weight of 3. So we add those two entries into our table. And then we say, what's the next biggest one? Well, it's AD at 4. And then we've also got BC at 4. So we put both of those down as well. So now the table is finished, I can start looking for the smallest numbers, and I'm going to redo the network with only the vertices there. And I'm going to start with the smallest edge and draw a line between those vertices. Well, our table shows us that BD is the smallest edge, and therefore we draw a line between B and D. In step 5, I continue to draw edges in ascending order of weight from my table until all vertices are included. I'm going to check at each stage to ensure that no cycle is created. If a cycle is created, I'm going to ignore that edge. So therefore, I look at my table. AB is the next item, so therefore I draw in AB. BE is the next one, I draw in that. CF is the next one, I draw in that, and EF is the next one, I draw in that. When I get to this stage, I can see that all the vertices have been used, so therefore I'm going to put a little red line underneath the last one that I used. I now add up all the numbers above the red line, and I find it is 2, 4, 6, 8, 9. So therefore, my minimum spanning tree is shown in the diagram, and it has a total weight of 9. Now we'll do a second example. Here's a new network with the edges showing in black and my weights showing in purple again. So I'm looking for in step 1, the smallest weight. I'll look at that. I've got 2 weights, both of 2. So I'll start with AD and 2, and I'll write that down. I'll now write my other weight of 2, which was for BC, so that goes in. Then I'll look for my next lowest weight, as it says in step 3, and I have AE of 3 and CD of 3, so I add both of those to my table. My next lowest weight is ED, which is 4, and then my final weight is AB, which is 5. My table is now complete, so I'll get rid of the edges and I'll get rid of the weights so that we've just got the vertices showing. Now AD is my minimum edge weight, so therefore I'm going to join AD. BC is also like that, I'll join BC. AE is the next one, so I'll join that. CD is the next one, I'll join that. Now I have all the vertices included, so I'll put a little red line under my CD, and the diagram shows our minimum spanning tree, and by adding up the numbers above the red line in the table, I know that the weight of the minimum spanning tree is 10. Now for Prim's algorithm, it finds a minimum spanning tree starting with a pre-selected vertex, and then it keeps adding the edges with the next smallest weight at each step. Prim's algorithm is most useful when a path has to be selected from a given starting point. For example, if we're making deliveries from a single warehouse, or visits are to be made to several offices starting from a central location. So how to implement Prim's algorithm? Well, we start with a network diagram with weights and vertices indicated, and I'm also going to copy down straight away the vertices in a separate diagram. Now select the vertex. Now I'm going to start at vertex F for no real reason, but it might be that has to be my central depot that I'm working from. So now I'm going to list in a table the edge weights to all vertices linked to that selected vertex, which is the F. So my edges from F are FE with a weight of 5, FB with a weight of 9, FD with a weight of 18. So the smallest weight is for FE with a 5, and so I put a little circle around the 5, and I join in my second diagram F to E. Now my new vertex that I'm adding is the E, so I'm going to look at all of the edges that emanate from E. So EA has a weight of 12, I'll put that into my table, and ED has a weight of 15, I'll put that into my table. So now in step 5, I'm going to repeat those steps 3 and 4 until all vertices are included. Well, from the new numbers that we've got in there, I see that FB has the lowest weight of 9, so I circle the 9 and I link F to B. As B is the new vertex that I've added, so I've now got to put in the other vertices that stem from B. So BA is 11 and BC is 8. I then look at my table of values which aren't circled. BC happens to be the next one, which is the lowest weight of 8, and so I circle the 8 and I add into my diagram the edge BC. So now I've got to be able to look at the edges that come from C. Well, CB is already there, so the new one is CD. So I put that into my table with a weight of 10, and then look across my table to say which is the lowest not circled number. So it's CD of 10, so I put a circle around 10 and add the CD edge to my diagram. From D, I already have DC, I just used that. DF is already there, DE is already there, so I can't add any more information to my table at this stage. And so I look along my smallest number. BA is 11, that's the smallest. Now I join B to A, and I notice that all my vertices have now been used. So I have my minimum spanning tree, and the total weight of it is the sum of the numbers which I've circled, and so that's 43. Nice and straightforward. Also, I notice that I have 5 edges selected in the tree because there are 6 vertices, something we talked about in a previous video. The number of edges is 1 less than the number of vertices. So in summary, there are 2 approaches to identifying a spanning tree with minimum weight. One is Kruskal's algorithm, and it starts with the smallest edge in a network. The other is Prim's algorithm, and it starts at any vertex which is selected. And the selection is especially based on the logistics of the path having to start at a given location, or when a network must start with a particular task. So there's our approach to identifying minimum spanning trees. What we're going to do in the next video is to extend our understanding of trees to determine the shortest path through a network which does not necessarily use all vertices. So consolidate what you've learned here by doing the test yourself questions on the website drjoesmaths.com. Hit the like button and subscribe if you haven't already, because then you'll get notifications about new videos. Good luck. See you soon.